conscious of the fact that it is a holiday weekend. Of course, today itself is not a holiday. And again, those who may be getting this, in Guyana and stuff. So tomorrow and Tuesday, Monday and Tuesday are official holidays. But like the Caribbean, then, I guess, like I guess I would say Caribbean because the same feeling is normally had by anybody who, and even probably Americans or whatever. Like when you have a Monday being a holiday, fine. A lot of people get things done on the weekend anyway, and that's all good. Remember, I always say, I always practice the same thing. Um, do what you like doing. Spend time with your family if that is what it is, right? But don't do the same thing for the whole day. Now, I always like to do different things in the same day. So like you could have an hour class, you could have, a 2 hour family get together. You could be safe if you're going out tonight. Of course, this is Sunday before the carnival. Anyway, but yeah, do everything in one day is what I am a big believer of. I was up this morning early, washed the car, that sort of thing. Went to the park, had a run, did about 90 push-ups, come and prepare work, right? And so every day is like that for me. I mean, as much as I could, I try to get, different things done. And even though, in your work day, and of course I do work late, those who know me, I work sometimes at 8 p.m. in the night. But as long as we could then, like on a day like today, you try to spend time with everything then, with work and family and getting stuff done for yourself, etc. as well, right? So nothing is wrong with that. And without any further ado, let me start so I could finish off my part of it for your day anyway. So I had a look at the syllabus and I decided to start with it. I hope you can see it. Um, I believe this is the last big chapter. Now, where we are at on the syllabus, if you can see there, process, hydrocarbon process safety two. I wanted it to physically see it because you can see where we are on the syllabus, then it's kind of low down, isn't it? I mean, the syllabus is here. If you look at where the cursor thing is here, right? Just let me do that again. And somebody is coming in, right? So it's kind of low down. Chapter 4 and chapter 5 are very short, right? Or element 4 and 5 are kind of short. Um, I had done it in like half day
I'm not
when I did it
totally worried, but
face to face, via face to face classes anyway. I'd finish it in about just about an hour and a half anyway, right? So I know today's a carnival kind of thing in Trinidad here, but at the same time, I wanted to, and I'll mention it on Wednesday, I wanted to start using the book. So we had given like an e-copy of the textbook, an online version of the book. And sometimes I've just seen psychologically, sometimes when the tutor doesn't use the book, the students don't use the books. I've realized that that's like a thing with Caribbean people. No, me, not me. If a course had a book, I would have read the whole book, right? I was given the book, you were given the book at the start, right? The online version anyways. I would have read that out anyway. But everybody's different now. So today, I'm gonna go to the PowerPoint, but I want to reflect on certain pages in the book. And that is to tell you that, well, you have to study. And studying, yes, I would say is always the PowerPoints first because they are written to the syllabus. But you could always read to supplement yourself, right? And eventually, I want us to start using more and more of the book at the end, right? And so just to let you know, I do that with all my courses. Those who know me know that. When we did process safety, if anybody did that here, I did the same thing. The last couple of lessons were straight from off the book, right? And so it's a way, like when you now start, you don't want to know, okay, like we just reading book because that's kind of boring. Most people tend to think if that's the case, we could have done it on our own. But as you start, then you get the lessons. But coming down, and I do believe that there's a place for you knowing, okay, like you need to do some extra reading and stuff, right? So I know today, like I said, not everybody's here, but I'll try that technique today. It's going to continue next week, Wednesday, which is also Ash Wednesday in Trinidad. It's not a public holiday, but again, locals tend to take that off as a day off. But we have classes on Wednesday, and I'm gonna continue more and more, and you'll see by chapter 4, 5, I'm gonna come off the PowerPoints altogether, right? I do that for all the other courses as well. It's just a way of telling you then that that you have to, because as I say, psychologically and even physically, like I remember having classes like face-to-face classes, and when I had other lecturers, of course, right, and different courses, um, we didn't have oil and gas then, so this is not for oil and gas, but we had a lecturer, and I remember coming into his room and seeing all the books closed. All the books were closed, right? Every single book was closed. And I had to say, well, we need to start using it, because the idea people got was that the book is not important. And yes, it is. I mean, all books are. Once is a book for the course, right? But I know there's a kind of disease in Trinidad, which is everybody wants the book, but then nobody ever reads the book. I think I have that same disease, as that, Um, I actually bought a book. I don't know if I shared that. I bought a book. So I don't just do academic stuff. I told her that, right? Like I go park, I do basketball, cycling, whatever have you, right? So I bought this really good book about a year ago, and it's been haunting me because I haven't read a page of it. And today I was looking at a video, a motivational video. I normally look at them in the morning, like when you get up to get the push-ups and stuff going now, right? And I heard the person, I think it was Denzel Washington. They have lots of motivational videos. I'll probably post one for you all day, right? And I heard him mention the book, and I was like, man, about 6 months I've had the book and I haven't read it. So I'm guilty the same way, where like we have this thing about getting a book but not using it. And so I have the same thing. So I told myself after class today, I have another class, but I told myself today after the second class, I'm gonna go in the office of the book and bring it home, because I feel I will be able to read a couple pages at home, right? It's a very powerful book. I shared it here. I mean, if Denzel Washington and these guys could actually mention it, I think I invested in it, but the thing is, I just held it as a hard copy, and I never even opened a page in it, right? So I'm just as guilty to blame as that as anybody else. All right. So what I wanted to share, let's just look at the syllabus quickly. So what we're going to look at today, 3.1. This is on the handout, but as I'll show you it here, right? Failure
Yes,
modes. Yeah.
excuse, I'm not seeing the
Oh,
PowerPoint open on the screen.
wow. Okay. Thanks for saying. Are you seeing the syllabus in the background? It should be saying content right now, failure modes. Yes.
Okay,
Okay.
yeah.
It's back up. Okay, good. Okay, good. Yeah, that happens sometimes. Thanks for saying, we normally sometimes what the teacher sees is what not necessarily that you all see, right? So we look at that failure mode, creep, stress corrosion, cracking, thermal shock, brittle fracture. So everything you see here, that's what I tell you. Like if you all just go with the handout, you'll be safe now. But some people don't believe me. Like if you watch this here and you watch the handout, we wrote the handout to suit the syllabus, right? So like if you're on the go, I used to always have it. I used to always print my handouts and I have it on the go. If I'm waiting in the car, right? Well, not the car I have now, but if I was waiting in the car, um, I was waiting in traffic, I would actually just watch it. I'd actually just cast my eyes down and watch it, right? I would, if I'm at the bank, if I was in a business place and I waited, I carry my hand out with me. And you'd be surprised to know, like in the bank, you read out the whole line. I mean, like the whole handout anyway, right? If you're waiting on somebody or whatever and you're waiting in the car, you read out the whole handout, right? And it was a way of saving time, right? Anyway, so just pay attention to the heading, right? Safe operating envelope, use of knowledge of failure modes in initial design, failure of the angular rim, bottom rim of the storage tank. So when you see it on the slide, you can remember, okay, well, that was ready from the syllabus and it's straight from the syllabus, right? So don't ever doubt your handout, right? But the handout may not be all. So what I said today, I'm going to kind of try to incorporate the book a bit with this so that you'll see. Other types of failure, well, failure, the need for regular well inspection and non-destructive inspection techniques. I think that's how far we'll reach today. I don't know we're gonna get into emergency shutdown equipment and systems 3.3, but if today class doesn't convince you to print your handout, 6 slides on a page, you could print them out totally, right? You could print them if you want to print them. Let me open the PowerPoint. If you want to print them, you could print them 6 slides. Like when you go to print it, print 6 slides on one page. So it ends up being less pages now, so less money for you to spend. right? The 6 slides is fit nice on a page and you could still read it without a problem, right? You still read it without a problem. So that is me, like that was me studying. Anywhere I go, I had it. And again, with you all now, knowing that when I say me, well, that'd be my lecturers back in the day. But with you all now, the PowerPoint is written to the syllabus, right? So let's try to reach let's finish 3.1. Then I'll open the book a bit. I will kind of want the digital book, have a look at it. Just to see now that it could have more stuff out there that you probably need to start incorporating that into your reading as well. Right? So failure modes, 3.1, right? Outline types of failure modes that may lead to loss of containment from hydrocarbons. So failure modes, vessels, pipework, and equipment may suffer wear and tear in their material from forces applied on the material itself. These forces can result in creep, stress, stress corrosion cracking, thermal shock, and brittle fracture. These forces acting on the metal can be tensile, pulling, or stretching. So you could probably picture, if you're having problem with this, like a pipe or pieces of pipe or a pipe rack, if you know what that is. Pipes are normally stored in a pipe rack. You can probably picture something being lifted, maybe like a piece of equipment. So when a crane, if you want to think of it as that, has a pipe or a piece of equipment that is slinged up then, right? That is putting a force. There's a force acting on the metal, right? So if you have things like pulling and stretching, if the metal is always, that piece of equipment is always being lifted and lowered, right? So that's a force acting on the metals. We have tensile stress, pulling or stretching, compressive, pushing the metal apart, shear, two forces applied against opposite direction anyway, right? And so that could also work for the piece of pipe if you want just a simple example. So if you have a crane, right? So we have our sting here and we are going to be, raising a piece of pipe. What you should probably remember is that the pipe itself have like a weight then, right? And so let's say this is a 10-ton crane, and let's say this is a 7-ton piece of pipe, right? Of course, that's kind of heavy, but just saying, right? But what you need to know is that this pipe itself have a weight now, right? So the weight is acting down due to gravity, but the crane is lifting up, right? So you have those kind of forces acting on metals. Then if it's more than one pipe, so if you put it like this, if there's more than one pipes that are being lifted at a time, maybe in a rack, then you could have the metal rubbing on each other then, right? So shear, two forces applied probably in opposite direction. These pipes that are sort of, slinged up here, the weight is pushing down, but the crane, of course, is lifting them up, etc. Right? Um, let's move on. So creep is a slow form of deformation over time due to constant load or stress being applied. You can find that a lot of times, not a lot of times, but you find it, right? You find it in the latch of the crane, right? Or the hook of the crane. Um, Most of the times, if these devices are going to fail, well, I mean, it's only if you exceed the safe working load of the crane. If you exceed the safe working load, let's say this is 10 ton and then you lift in 20 tons, but then the crane could come forward and collapse. But most of the times when loads fail, is because of the latch. The latch have been worn, the closing mechanism then have been stretched and have been creep. And what is creep? Creep is due to all of that lifting over many lifts over many years, right? I know of construction sites where the latch doesn't close properly on a lot of these cranes. I know, and you probably know too, that to repair it is not too expensive, but it is expensive. And most construction sites may just say like just work it as is. But if it's defective, like it could stretch out then, right? Like it could break out then, right? Due to the force that was acting on it. So what is creep? Creep is like this slow slow deformation of that piece of metal from the original latch. You may have realized that it's not closing properly. And we call it a creep, right? Creep is that the metal have been stretched. And the thing with metals is that once it's stretched or it elongates a bit, it doesn't go back, right? It doesn't go back. Then, like to say, like an elastic kind of material, it doesn't go back, right? It will just stay a bit elongated. And then if you keep using that, it's going to stretch, and then, as you guess, maybe stretch out, right? So constantly stretch to a point beyond its elastic limit. That is a term we use here in terms of the breaking point. Permanently deformity or permanent deformity, accumulated weakness, right? Time and temperature dependent. So again, if it's not temperature, if this was just a crane in the sun or whatever, right? If it is, something that was lifted, something that was hot, maybe some sort of acid, that could, of course, escalate the fact that the metal may actually deform as well. So it may result in one or more failures. They have two failures here mentioned, but something called a brittle failure and a ductile failure. Well, a ductile failure is on the next slide if you want to get explained one time, but a ductile failure is one in which, like, you would see, like, if we were to draw just a hooking mechanism, right? Like, you could actually see then, you could actually see, like, where this then, if we just picture that alone, like that latch then, like, you see it stretch, right? You see it not looking, it looking deformed, as it is a permanent deformity, right? So if you could see it, that's said to be a ductile failure. Ductile means it has been stretched to a certain point, and a good way to think of ductile is like wire, right? They say, like, if you bend a piece of wire, right? But that's ductile. The fact that you can bend it, right? It's actually ductile. Now, brittle, you don't see brittle failure, right? Brittle failure, if you want to picture that one, so you can picture ductile as you can actually look at the latch. And anybody can say, like, this thing seems as if it's probably going to fail, right? But brittle failure, they say, happens in the metal itself, right? So ductile you could see, but a brittle failure, right? In the metal itself, yeah, I guess you could see it, right? But you'll have to take some sort of test, right? Some sort of X-ray of the metal itself. So the metal itself, what they say is that there is going to be like a crack inside the metal itself, and it's just going to snap on you, right? So like a brittle failure is like a ceramic cup breaking, right? Like if you have your teacup, all right, but let's mute some of the background noise. Yeah, if you have like your teacup or you have like a glass, some people have a glass table. I mean, you must have seen some of this on maybe sometimes they have it on funny videos or disaster videos or whatever. Not really disaster, but like home disaster videos where somebody has a glass table. They would put like a hot cup of coffee on it, and then see, like, you see like the glass shatter, right? So that is also a type of failure, but it's brittle failure. Like you don't get warning of it. Again, picture like your coffee cup or your teacup. If the handle was to break or God forbid it fall and it break, when you look at it then it cannot be joined back, right? So that's brittle failure. Ductile, it could actually heat it. Like a ductile material could actually be heated back and put back together, right? But brittle fractures and failures and stuff, you really don't see a sign of deformity. Like that glass table that you put your hot cup of coffee on, and then maybe somebody wears something cold. You don't see the cracks, then it just shatters, right? Or at the time you see the crack, that's the time it failed one time, right? There's no prior warning where you can come and look at it like a deformed piece of metal and say, okay, this thing looks as if it's going to stretch out. That's ductile failure. Brittle fracture really gives you no warning of the failure itself. Now, you may need to describe it. I think some of it is in the next slide. But I know of questions that asks, like, how do metal fail? So that's why I underline these two now. We have brittle fracture and we have ductile failure. Ductile gives you a warning. Brittle happens in the grains of the metal itself. You have to take some kind of X-ray, some sort of test to actually see that. But naturally to the human eye, you don't get a sign that the thing is going to fail right? It just shatters on you, and that is a brittle failure anyway, right? So failure mode creep linked to deformation in turbines and can cause rupture in fractured steam lines is the best control in the design stage by the use of metals such as chrome, molybdenum, steel, that's how they pronounce that word, molybdenum steel, and that type of steel is like you can think of it, as a stronger type of steel. It's one that has been plated. They did mention chrome, right? So they put like a layer of chrome on the metals, and that could, of course, reduce things like corrosion and things that could lead to failure. Of course, all metals do fail once you cross their yield point. All metals fail if you cross their like their boiling point, right? Or the point at which it could fracture. For steel, that's around like 400 degrees Celsius. You may chrome it, you may put extra layers on it. It will give it a bit of extra resistance, but nothing in this life is actually 100% bulletproof then, right? A steel beam, a solid steel beam will still be compromised at 400 to 600 degrees Celsius. I'll say that again. Yeah, steel beam. Once it reaches 400 degrees Celsius to 600 degrees Celsius, that's the end of that, right? But you could do things that, like I said, you could paint it, chrome it, whatever, and those things work best. But just remember, nothing is 100%, guaranteed. Then at least not in this life anyway. The only thing 100% guaranteed down here is actually death, right? But everything has failed. Then no matter what you do to it, it's gonna fail anyway, right? Stress is the internal. Let me take off some of the drawing I have there. I'll leave anyone on the left hand side, right? But I can take this off. So stress, again, this is the same formula I saw in the book, same thing I saw in the syllabus. But let's try to put some work behind us and then we'll look back, right? At the book and stuff, right? And then at the passive and whatever. Stress is the internal resistance to externally applied forces. It is the force applied per unit area. So that's a good thing to learn. They do like these kind of definitions. Strain is the alteration in shape, size of whatever you're looking at, resulting from an externally applied force or forces, right? It is the amount of material stretches compared to its original size. I saw this on the syllabus, I've seen it in the book, and I put it here for you all to write. Strain is the ratio of the extension. So how much did it increase by over the original length, right? So if you had you guess a 20, no, I'll take something simple. I guess a 10 feet piece of pipe, and maybe that pipe was used to pump steam. So what was in it was hot. Even oil, I mean, oil has a temperature. Like production oil I'm talking about has a temperature. So, if they did quality testing on that piece of pipe, now they wouldn't really do that too much in Trinidad. Only if piece of it fail, like what we have in Destiny right now, if a piece of the line fail and then they replacing the line, then I guess if the company is being proactive, they could send the piece that they took out for testing, right? And they could test it down. They could use like a calibrator or a calibration device if they're able to check and say, okay, look, I mean, what caused the join in? There's like a clamp, like in the oil and gas field, as some of you would know, like a pipe is not just one piece of pipe. A pipe is pipe fitted on to another piece of pipe with threaders, and that's pipe fitted on to another piece of pipe with threaders as well. So if they examine any piece of pipe, they could actually look at the threaders, right? Those of us who do this would know this quality now. They could actually look at the threaders. When a pipe goes into service, the quality department look at the threaders, the cuts in the pipe then to tell if the threaders are okay, and then that piece of pipe would have passed quality test. So by extension, if the pipe fail and they want to figure what went wrong, they could use something like that. And they could probably get from the 10 feet, you probably get, 10, probably 11 feet. But that's a big stretch, right? So it wouldn't be wouldn't be so bad to actually cause a clamp or a fitting to start leaking. It maybe like 10 feet, 0.1, 10 feet, 0.2, right? 0.002. But that extra stretch then is what caused the threaders not to hold, and when the threaders didn't hold, that's where the oil started to shoot from, right? Those of us have actually done these things. Strange enough, they were things that I did. I never knew it would have been beneficial back then. Like when you were clamping lines, we used to clamp a line. Clamping a line mean if a line have a leak, right? If anybody know that part of it here, clamping a line, they would actually put a temporary clamp on the line to actually prevent the oil from leaking. And then uh, post clamping the line, they would have the pipe fitters come in and, of course, isolate the line and isolate the well and then change the piece of pipe that is off, right? Nonetheless, I think this is a nice thing to learn. Change in length over the original length will give you the definition of strain. I can see these things. I can see they say define what is stress, define what is strain. Identify two ways metals can fail, brittle and ductile, maybe even describe one of them, right? And so these are not weird questions. These are all really good sort of questions anyway. Whenever I start, I always thought we'd reach further, but the explanation do take time, right? Failure mode, effects of loading. Materials when subjected to excessive loading can become permanently deformed and that they cannot return to their original form. This is called plastic deformation. Tensile strength is the maximum force necessary to cause fracture. Remember, tensile is like pulling apart. Compressive is pushing together, and shear is like metals rubbing on each other. Can happen in a pipeline or a pipe rack, right? A lot of the lines in the onshore oil industry then it's like in a rack, right? And you have like more than one line, so each line is pumping, right? I can think of examples like that anyway. So permanent deformation can also occur if the material is stressed beyond its yield point. The yield point is like the breaking point. Stress on the body of the vessel or pipework system can arise from periodic fluctuation in operating pressure, right? Again, if anyone is, and you don't have to be too much in the field, you could probably think about like your water lines at home in the Caribbean, right? Sometimes, right? But the water authority here is called WASA, of course. So sometimes, the lines are running okay, right? The lines, the water is there okay, but then sometimes you see like there's an excess pressure on the line. You hear a sound, you go outside, you check your lines, you notice, okay, well, something is weird. The lines are vibrated, the lines are sometimes, vibrated heavily, right? And then, okay, it's sort of, thought about that maybe the water authority put on extra pressure, right? So some of these things do happen. Of course, these things in the oil and gas field supposed to be regulated, but they could have like their pressure valves, their pressure relief valves, their pressure gauges, those things can malfunction. It may be the operator error of a gauger in the oil and gas industry, not online, onshore industry, we have gauges. Sometimes gauges determine the flow rate. It may be a human error, something that there's extra pressure on a line then, right? Temperature cycling, vibration, water hammer. I'll explain that one. Fluctuation of external loads, fatigue on the metal itself, exceeding the yield point and endurance limit of the metal, right? So water hammer, I don't know if we discussed that before, but it's like the sound of the fluid in the line. It's not really often always water, it could be oil. But if you've been around them, you know that they kind of make a sound, right? Like when okay, they were like when the pressure is turned on, they make a sound. You probably hear it in your water lines as well sometime. You'll probably hear, like okay, the pressure sounds a little harder, the lines are vibrating, etc. Right? So all of these things could happen, and this could lead to stress on the metal itself, causing joints, any point of connection to sort of become weaker. And of course, if it's the metal itself being stressed, like the threaders themselves, they may become loose, resulting in a loose fitting, a loose color, and then, of course, some sort of leak anyway. So we have a little diagram here of them. Tensile strength, like I said, the crane, because we still have here, pulling on a metal surface, but the metal itself is heavy. And so weight of the metal is also a force, right? In the world of physics, weight is measured in newtons, and newtons is the units for force. So there's a force acting on the metal, raising the metal, but weight is actually measured in newtons, right? So if it's with physics and they say, well, what's the force? But you have the weight is the force, right? So that's kind of a physics concept anyway. Compressive strength, two metals pushing on each other, share the pushing apart from each other, right? Tell me if you're okay with that. I didn't want to pause and look at the book as yet, so I um wouldn't pause as yet, right? I would just keep going anyway. I wouldn't pause as yet. But I hope you remember some of the concepts. When we open the book, you'll see it, right? You'll see stress, you'll see strain, you'll see some of this, right? And that you can see it there as well. Stress corrosion cracking. So occurs when the following occurs together. You have a susceptible material. So maybe you have a metal that it didn't really quote, they didn't put, I mean, from our first class, they didn't use an anti-wetting agent, they didn't treat it for corrosion, so you have a susceptible material. You have a corrosive environment somewhat close to the sea, or maybe on the offshore industry, you have the salt from the sea. Um, I mean, like anybody, I mean, we live on an island, right? The majority of us here live on an island. I think we have a couple of Guyanese but we live on an island, and like I remember, I mean, I don't live there anymore, but where I grew up then was Lucero. There's a place called Lucero. Well, we say Lucero. The proper thing is Los Iros, but everybody from there say Lucero. And I remember people would say, like, if you had a vehicle, it would tend to corrode more than like if you live close to the beach. Like we see signs of rust on it more than if you live further from the beach, right? Now, I had an experience like that. I don't know if it's still, I mean, it probably still is true, but I don't really live. And so, like, I had a first car and that did kind of rotten down, but I don't know if that was probably because of my lack of maintenance or if it was just living close to the sea then, right? If anybody have a similar experience. And then my father had a van. He had a new van I mean, he still is alive, but that was when I was growing up, and he bought a new van from Massey, new brand, and that van actually rotten down as well, right? And so that's my experience with it. I don't know if it's because we were close there. I don't even. I mean, I know he used to take care of it, but to me, like vehicles don't rotten that fast. Then the reason why I say that is because I have two cars, and well, I had another one, but I sold it last year. And I've had that car for more than 10. To be honest, that car was going in 18 years, 17 years, and that car was good. There was really no sort of rot to the body of it. But that is because I'm actually in San Fernando now. So maybe those are the thing. Maybe if you do live in some kind of, sea type, shore environment, maybe it is that the salt would attack the metal because that is what the evidence sound like. But of course, it may be that we need more people to kind of see if that is true. Doesn't have to be in class. I just said maybe that's something I heard about, but then haven't experienced it. Maybe it is somewhat true. Trinidad is still small, so no matter where you go, I mean, you're still surrounded by sea, but at least it's not on the sea shore then, like the sea coast then. It is not what San Fernando is anyway, right? So a corrosive environment, enough tensile strength to induce the condition. Examples include caustic embrittlement of steel boilers and stress corrosion cracking of stainless steel in the presence of chloride iron. Um, so I won't go too much into that. All you need to remember there, I mean, I don't know if anybody want anything in that, but um, whenever you separate an atom then, right? Or should I say a molecule, it goes into its ionic state. So this is actually not spelled incorrect. This is how you pronounce this. IONS is actually ions. That is when you separate a molecule, you get the ionic state of it, but the ionic state of it is corrosive, right? So if you read this over, the chlorine ions then is what attacks the metal. At any ionic state, like even if it's split water, you'll get H. If it's split water, right? I'm gonna put that up here. And there are ways to do it. There's a process called electrolysis. So split water. H2O is water. But if you electrolyze water then, right, you're gonna get H and O. two H's, and each one carries a positive charge. But once you get to the ionic stage, those things are corrosive, right? So examples include caustic embrittlement of steel boilers and stress corrosion cracking of stainless steel. So imagine that. I mean, stainless steel, but like I said, nothing is 100% proof in this life. So even if it's stainless steel, if you're in the presence of chloride, iron is going to attack that stainless steel. It's going to corrode it, right? Nothing here stays. Nothing here stays, right? Metal corrode. What's the other saying? Rot. I think things like wood and stuff would rot. Metal corrodes. Nothing really stays forever. And even if you treat it and whatever have you. Maybe diamonds. I'm not too sure about diamonds. Maybe diamonds. Diamonds and cockroaches, maybe. Right? Maybe those are the things that stay, right? Diamonds and cockroaches. I can't see they're going anyway. But the things that human beings interact with and metals and stuff, I mean, they don't tend to last, right? The best car you have 10 years ago is going to start to corrode 10 years from the time that you bought it, right? And so that's the nature of life anyway. Right. And of course, like I said, it have to do with nature. This is chloride ions, and that's just how it is. Things don't last anyway, right? So stress corrosion cracking. Stress corrosion is worse in corrosive environments at elevated temperatures. Amongst alloys, I can explain that to the end. Aluminum, copper, susceptible, everything is susceptible. All of these are ionic state, chlorides, nitrates, and ammonia, right? But like you have to get it to the ionic state, right? Ammonia is NH3. If you split it, it's going to be three H's and one N, right? Nitrate is one N and three oxygen. So can be prevented by selected materials not likely to be affected by these chemicals. And if it's not that chemical, it's going to be affected by good old-fashioned oxygen anyway, right? Can't stop corrosion. But alloys are more susceptible because alloy is not a pure metal, right? Like certain metals are like pure metals then, so you have this is alloys of aluminum and copper, right? But you can have like pure metal, like certain metals. I could call some for you. Of course, some of the best ones that tend to be very durable, right? Which is why the world is after them. Gold, silver, right? Platinum. So it have certain metals then that if you the pure state of it then could withstand heat. And of course, the value of them financially as well. But they are durable metals then, which is why I said the world is after them, right? So whatever you have, don't give it up. Don't give it up, right? You ever wonder, did anybody ever, like anyone of your experience during the pandemic or just post pandemic? No, like prior to the pandemic, there were people coming around trying to get whatever little bit of gold you had. They were sellers, but they had to be working for somebody, and they had blenders and kitchen appliances, and they were trying to get. Did that ever happen in your village? Anybody know what I'm talking about? So it seemed to be like the people, some people knew that, and this is the thing about gold. Gold would withstand, like a period of recession. Then gold doesn't decrease in value. If I ever had the money again, I probably would invest in gold, right? But if you ever have a chance to buy gold, buy it, right? And if you have a chance to store stuff and because gold doesn't recession, Donald Trump, World War III, whatever, gold survives, right? Money value, what happened to the TT dollar, the Guyanese dollar, the Venezuelan dollar. Gold isn't affected by dollar value then. Goal is goal. I don't know if you understand that, right? So I don't know if you all anybody could have witnessed to that. Like Trinidad a couple of years ago, there were people coming around trying to get whatever goal you had. And they were selling sort of more or less household appliances and I think people kind of understood then the value of
Still,
gold
they're
anyway,
still
right?
doing that. They're still doing that. Mostly the Venezuelan, it's still happening.
Oh, okay. But try not to part with your goal, right? Try not to that is common sense. Try not to part with your goal financially. Like, have you been looking at the news last week? Did you all see the news with Donald Trump and Zelensky and Ukraine? If not, go and look at it. right? Some strange times we living in. But America is, I mean, like withdrawing a lot of stuff from around the world. Environmental agencies are no longer part of that. Ukraine, they're not back in Ukraine anymore, right? But I guess change is how it is. I mean, everybody have their opinion, right? But the world is changing. That's the thing, though. The world is changing. If it changed back, for those of us who looked at it last week, I think Donald Trump is going to rename the Gulf of Mexico to the Gulf of America. This is a true thing, right? It's true things here. So the world is changing. Whatever you have of value, try to hold on to it. But like I said, in terms of metals and stuff, as we're talking about gold here, don't part with your goal, right? Whatever, happens, that is still of value anyway, right? So stress, corrosion, cracking, and like I said, gold is like a pure metal. It wouldn't go through corrosion. That's one of the beauty about it. And of course, other precious metals as well. You heard me mention things like diamond and platinum and stuff as well, right? So stress, corrosion, cracking mostly occur in alloys, which is a mixture of two metals, right? Rather than pure metals, and frequently found where there is exposure to chemicals. Example, copper and its alloy crack when exposed to ammonia. Controls selected materials that are not susceptible to such chemicals. Annealing after fabrication of wells. Um, I guess I have to tell you what it means, but and so uh again, you probably may have to picture somebody welding here, or if you have seen somebody welding. So if you weld a piece of metal, I'll just draw something here for you all. If you weld a piece of metal, right? That didn't come out the way I wanted to come out, right? You can actually see the welding joint there. You can actually see where it was welded on, right? However, you can actually do something with that in which you blend the welding joint blends into the metal. That's called annealing, right? So annealing is actually heating and cooling. Heating and cooling. You could think of it like that. But the purpose of annealing is to kind of let the weld blend into the metal, right? It's like a period of heating. Like you kind of heat here then to let it blend into the metal itself, right? Yeah, you heat and you cool, you heat and you cool, you heat and you cool, right? So in a way, if you did heat the metal to get it to be flush, then that could be a way of getting rid of. If you did sort of weld here for corrosion, let's say this piece was corroded, but you're not going to leave it like that. You want the metal to blend back. The piece that you welded on, you want it to blend into the metal itself, right? So that is the annealing after the fabrication of welds, right? So when you finish now, you'll get like it looks like a finished product. You may have to take your grinder and whatever and finish it up, but the process of annealing is heating and cooling to get the metal to blend back the molecules. If you look at this I'm not too sure if that is chemistry or physics in that kind of perspective, they talk about the process of heating and cooling is going to blend the molecules back together, right? So that's a good thing to do to avoid, like corrosion. If this was a piece that was corroded and then you weld it back on, this is a good control. Maybe, folks, you should learn the word, right? Because you could all say painting, you could all say choosing a method that is not susceptible to the environment, like if it's salt or salty or whatever have you. But what about this? What about saying annealing after fabrication of wells, right? And so that's a very good control. Hopefully you understand it a bit. That's the simplest and it's actually the most complicated. I don't think it gets deeper than that. If you research it more, you'll see where they could show like a metal heating and the molecules kind of merge back into one, right? But the process of that is to get a flush product, right? As opposed to leaving this kind of grain on it where you can actually see the weld itself. And of course, that's a point of weakness. So you do want the metal to merge back into that piece that you would have added on anyway, right? Take a note of it. Take a note of it. Take a note of it, right? When we go to the book, we could see if we can find it, right? But you know what it is, and I told you what it is, right? It's a good control. Instead of saying, we could say things that you say, painting, chroming, whatever, but you could say annealing as well. Thermal shock, it is a mechanical load caused by a rapid change of temperature of a certain point. It can also extend to the case of a thermal gradient, which makes different parts of the object expand by different amounts. A brittle fracture is an example. How can this be avoided? So I think there are two things on this slide. First of all is thermal shock. So thermal shock is caused by a rapid change of temperature. I guess like in the making of these clay jars or clay pots here, it would have been hot, and then if you subject it to like a sudden cold, it could result in a crack, right? Well, if it is clay pots, yes, it would fail by brittle because brittle doesn't give you a warning. Like you don't see it deform and you just see the piece that break off, right? It just breaks off like a coffee cup then, right? So the brittle piece is okay. But I've seen this one to define what is thermal shock, right? So I don't know if the definition would stop here. If you're learning it, you have to say something like it's caused by a rapid temperature change, right? And again, that change may cause a deformity. Most of the times, thermal shock, right? I think it's going to lead to a brittle fracture because even in one of the glass table at home, or I mean, not saying home, but most of the home videos will have it like that, right? Like where somebody put a hot cup of coffee on a glass table and then somebody may rest a cold drink and then the whole thing cracks, right? That is still thermal shock because it's actually hot and cold. It's hot coffee and maybe a cold Coke, right? So it still is thermal shock. And the way it feels via brittle fracture. So brittle fracture is a sudden, very rapid cracking of equipment under stress where the material exhibit little or no evidence of ductility because you don't see it bending and plastic doesn't bend. Glass doesn't, sorry, not plastic. Glass doesn't bend then. Anything that bends is ductile, which is like wire, right? Like electrical wire, right? But brittle doesn't give any warning. There's no ductility or plastic deformation before the fracture occurs. Brittle fracture is often caused by low temperatures or high temperatures or a change in temperature. There is a characteristic crack or loud bang as the fracture occurs. Factors that promote brittle fracture: low temperature, impact loading in the starch of the lift equipment, and we spoke about that one, look, it's still here. Residual tensile stresses. This is a strange one, but I guess it's an answer. Occurs during fabrication or the manufacturing stage, resulting in a preloading of the material. So that's a fancy way of saying that there's a manufacturing defect, right? So you could have bought, I guess, one of the hooking mechanism. You could have bought, I guess I'm trying to say like maybe some sort of lifting equipment, but there's a defect in it. Then to your eyes, you don't see the defect because it looks good on the outside. They would have painted, varnished it, whatever. They would have, done their sandblasting in it, whatever. But inside of it, something is wrong with it, and that will be residual tensile stresses, right? Inherently brittle materials such as cast iron, glass, and ceramics could fail via brittle fracture. Brittle fracture does not show sign of deformation or corrosion, and we covered that already, right? Brittle fracture of welded components is dependent on the thickness of the welding plate. Again, residual stresses present after fabrication and the operating environment. If it's, sort of hot, because we're talking about brittle, hot and cold, right? Then that if it is in a workshop, if it is, like a machine shop type environment, and what you're working on, like the metal, I mean, like there are companies in Trinidad that do this, right? And then so like they make products from scratch, right? They make pumps from scratch in Trinidad and Tobago here, probably in Guyana too, right? Some of it is imported. Some companies do actually make them right here. So if you're in that kind of environment where pieces are being made then, but then it's being put together, then you can have, the operating environment being one that is hot if you're into the furnaces, hot if you're into welding, but then cool if you're into cooling, cool if you're into painting, right? That sort of environment anyway, right? I'm moving on. So this was on the syllabus, if you remember, safe operating envelope. I think the last point is the better point, right? This one down, but I'll read at the top, right? So the safe operating envelope refers to the set of limits and conditions within which the process operates. It must be operated to ensure conformance with the safety analysis upon which the process plant operates, which can be monitored by or on behalf of the operator, technician, or supervisor. It's kind of long. I think the second one is a better one, right? So if they ask you to define, I've seen that one, define what is a SOE. Those who saw the syllabus when you started, this is right there on the syllabus. So it contains parameters that contains a controlled reaction with prescribed upper and lower limits enabling safe operation, right? So the truth is, everything have a safe operating envelope. All metals, then, if we continue with metals, all metals have a safe operating envelope. All metals that have a yield point, and that you can think of the crane then, if you find that's a harder way to think of it, right? You can think of the crane. The crane have a tonnage, right? So the safe operating envelope here, we could say is like from 1 ton to 10 tons. This crane is good for that. This crane is good for that, right? 1 ton to 10 tons. But if it's at across the 10 tons, you probably be okay now, right? For those of us who know, you probably be okay, but not too much, right? If you say 11 tons, 12 tons, fine, you probably be okay. That's not too much. You may start to strain the metal, and that's when the metal is going to probably start to show signs of, over years, if you was doing that, it may show signs of deformity, right? But if you put an excessive amount of load on this, if this is a 10-ton crane, and then you lift in something 50 tons there, well, then you would have passed the safe operating envelope, right? If the controls on you give way, if all of this come crashing down, it's because you'd have passed then the safe operating envelope, right? But nitty-gritty wise too, I mean, that's a big example. That's a simple one for you to understand. But nitty-gritty wise, remember all metals have, like a certain weight then, a certain yield point. Their atoms, their molecules that have a certain amount that they can handle, that they can take. And once you pass that, you get the stress, you get the strain, which was the formula I saw before, changing the length over the original length. So every metal is like that. Every metal have, a safe operating envelope. But you can think of it as simple as what we have here, because it's just a definition. I would advise you that you learn this one, right? That's the thing though, remember, print your slide, print your slide, print your slide. So whatever things, and the reason for saying it is not because I feel to say it, because I know it is a question. Define what is safe operating envelope. Certain things you have to come into memory. Certain things you can just read and remember. Brittle, ductile. They love thermal shock. Define what is thermal shock, right? Ductility, brittle, we mentioned that as well. These could all be nice definitions. What is creep? What is stress? What is strain? All of these are nice little definitions. You do have to know your work compared to the other courses that we would have done. Those of us who did other courses here, like you could rely on your book then for the open book exams, and the process people could rely on the answers being on the screen because it was a multiple choice exam. You all do have to study anyway, right? So what's the knowledge of the failure mode good for? Like, what is that knowledge good for if you know then that the material would fail over 10 tons? Well, they say it's to determine the safe working load, right? So if you know the crane capacity is 10 tons, but then you know not to exceed that, to determine the maximum pressure or force that can be tolerated, to allow designers to select robust materials for construction, ease of maintenance and replacement. That's a big answer. Most people wouldn't do that. To set specification limits of temperature, pressure, flow rate, thickness of materials that would not compromise the safe operating limit and safe operating envelope, right? So that's a good one, but I would have to change the example, right? Like if you know like a pump or a valve, I'll go to a valve, right? So on a line, I mean, we all have valves at home. You have them on your water line, right? Well, most of the times they are circular, right? Well, actually, you do have the kind of check valve now, anyway, right? So if you know you have a valve, so on this line, we draw this as a line has a flow rate. There's something called a flow rate. Let's say it's like 2 liters per minute. Yeah, that's how they check it, right? You don't have to know any of that. But 2 liters per minute, right? That's the flow rate. Well, the valve have to be able to take that then. Remember, this valve could be closed in the event there's some other work going on in the event that there's some other line, a lot of times they in the oil field industry have lines that go to many um manifolds, they call them, right? So if this line is required to be closed for another inlet of oil to come from another well, because if you don't close it, it may have backflow. Well, this line, then this valve must be able to take the flow rates. If you know, okay, the flow rate is 2 liters per minute, the valve have that kind of capacity, that's good. That's a good thing, of course, right? But of course, we didn't mention at the start of the class today, if there is human error, if there's an increase in pressure, so from 2 liters per minute, it went to 10 liters per minute, this valve could actually fail and blow out, as they call it, right? So the knowledge of failure modes or the knowledge of safe operating envelope, because that's where this came from, right? This didn't come by itself. This is the slide after safe operating envelope. So if you know the safe operating envelope is 2 liters per minute, well then you could set your flow rate there and make sure your valves are okay. Make sure the flow rate stays under 2 liters per minute. Maybe, of course they have valves that will take much higher pressure than that. And there's actually another concept that I'm not going to mention as yet, but there's actually something called like derating. Derating is this valve will be able to take way more than 2 liters per minute, but it wouldn't take everything. Then it wouldn't take, again, like I said, it's not going to be a foolproof valve. It'll be able to take way much more than that, but the valve will still have a capacity. The valve will still have an upper limit, right? It doesn't matter how good valve it is anyway. All right, moving on. I feel I'll leave some of my examples here because I think a scene we could actually use it, instead of having to draw back those things again. All right. This is the last thing in 3.1, I believe. Yeah. If those of us who remember looking at the syllabus at the start, failure of the angular rim. This kind of stuck out on the syllabus. If I don't know if you want to go back and see it, the syllabus just had it at the end there. Failure of angular rims. But I do think it have to do with knowing then that this is still part of the safe operating envelope, right? Like the designers of the tank would have known the weight then that could be borne or held by the tank, right? Anyway, let me read it from here how it is on the syllabus, right? So this is the name given to the bottom rim of the storage tank, right? The angular rim. So failure of the angular rim, this occurs due to the contents of the tank, such as high seawater or whatever, oil, whatever, right? Once, it's a weight on the base of the tank, right? Settlement of the tank onto its foundation can lead to corrosion. It's sometimes not an easy process. That's if you're moving a tank or you fabricate a tank somewhere else, right? For that reason, sometimes people do the fabrication on site, but they do move tanks as well, right? They move tanks one location to the next location, right? So settlement of tank onto its foundation can lead to corrosion, scratching, right? As the metal is settled from off the cranes and trucks and whatever have you, right? It's often never and it's never a slow process. The act of simply getting the tank down and the base still have a bit of friction involved in that anyway, right? The settlement of the tank onto its foundation can lead to corrosion as the joints and protective coating can be affected by the settling process during placement and movement. Contents such as high sulfuric content or sulfur content can lead to bacterial corrosion. Again, it depends on what you're storing in the tank. Sulfur there may come from oil. Oil actually have sulfur in it, right? Excessive movement can lead to mechanical failure of the rim and the bottom plates. Yes, right? Because remember those things. A tank is not one sheet of metal. You don't just get one sheet of metal. Maybe in years to come, or maybe the aliens have that technology. Because, that's what they say, right? Like for those of us who know, they say, but they don't call them aliens anymore. They call them aerial phenomena. Like people have, the American government have come out and said they have some of these things, and it's like one sheet of metal is like it was like one. So maybe they have that technology, or maybe we humans have that technology, but we don't say. But a weller then a tank is not just one piece of metal. It's like they weld the base, they weld the sides. If you ever look at a tank, it have all the weld joints on it. They weld the different rims because it's different metals they put in together, right? The bolts and the door, right? The tank door itself, right? So it's not one piece of metal. Maybe that technology exists, like I said, but it's not available to everybody. Certain persons or certain entities may have that technology. For now, tanks are not just one solid metal that suddenly became a tank. It is welded on piece by piece, layer by layer, rim by rim, till you get how high you want your tank to be, etc. Right? So excessive movements can lead to mechanical failures of the rim and the bottom plates, right? All right, we wanna kind of just look at the book a little bit, outline types of failures. Oh, it's not that long, thank God. 3.2. Remember I said I want to read 3.3, right? So 3.3 right there. Um, and this one is not that long, 3.2. Outline types of failures. We have the ways to do it. I think I took this straight from your book, right? Let's have a look at the book a bit. If you came in late, I told the class I wanted to start doing this for many reasons, right? Hmm, I'm not seeing it. Where did I put it? Give me a minute, right? I think Zoom does only allow us to share. When I open the syllabus, I think it replaced the book, right? Oh, got it, right? I know I had it open. Let me share it with you all. Hopefully it's gonna share. Funny thing is I'm seeing it, but you all are not seeing it as yet. Let me just see what's happening here. You can let me know when you're seeing it. I am seeing it, but I didn't see it on the share screen. Okay, I now see it. It's way down there. Right, so so I still want to finish 3.2, so I'm going to spend the whole time in the book. But today was hydrocarbon process safety 2. Those of us who hear the start, we looked at the syllabus and we pointed out exactly what was on the syllabus. But I made note of how far we were on the syllabus, right? If you have some time, go back and look. When I post it now, let's go back and look at the start of the lesson. We are pretty far on the syllabus. We have like quarter again to go, right? So I've started to say maybe we need to kind of look at the book a bit. Eventually, what I want to do is kind of go into all of the book then, right? So if you look at what we did creep, like the same set of things there. Oh, by the way, can you all see it? Can you all see yeah, okay, we have tensile compressive sharing, right? Some other things there. The book sometimes have more than the syllabus, right? But we write when you read the syllabus at the start, that's what we read, right? From the syllabus. A book always have more. Failure modes, we have stress, we have strain. I think the same formula, maybe the strain, change in length over the original length, right? So we're going down a bit. Not that I want to do all today. Brittle fracture is there, thermal shock is there. Look at thermal shock here, right? The effects of cracking that results from rapid and extreme temperature changes from hot to cold and vice versa. I think that's a nice definition, right? And the logic I was saying is that I always think the book have good information in it. The PowerPoint is written to the like to the syllabus, point on, but there's often more things I find that anybody can find some time to read, right? Angular rim, the name given to the bottom rim of the storage tank. This is what we just read. Meaning of safe operating envelope, right? So the process designer is trying to achieve a controlled chemical reaction that prevents a hazardous situation from occurring. The safe operating envelope defines the boundaries that contain the control reaction, right? In the safe operating envelope, safety is determined within the designer's boundaries, often at upper and lower limits. So you find that is what I put on this slide, right? But good stuff. That's what I'm trying to say, good stuff. And when you're studying, don't neglect the materials you have then, right? Other types of failure modes, or this is what we're gonna do now. Let me just go back up a bit. Let me see if we can pull something from here. I just read this paragraph here, right? The rim and bottom plate of storage tanks will corrode rapidly if the fluid stored in them have high seawater content, example, crude oil tanks. The seawater will corrode the base plates and rim faster than other parts of the structure, and pitting corrosion will be a significant feature. We did pitting corrosion on Wednesday. I'm afraid to ask if anybody remember what it is. So I'll just tell you, right? Pitting corrosion is if you look at the corrosion on the, well, if you look at it, you'll see like a sink. You'll see like an impression then. So that's what they call it, a pit. If you did actually get a microscope, a magnifying glass, not a microscope. I guess you could get a microscope. Nobody will actually get it. But if you get a magnifying glass and you watch, you see like pits, you see like holes, right? So that way that type of corrosion, they call it pitting because you see impressions on it then, right? You see how good, and what I'm trying to tell you is don't be afraid of your book. Those of us who did process safety and me remember the same thing, right? Don't be afraid of your book. If you did a degree, we'd open the book and take a read. The book just be a nice read. Don't be afraid of it, right? Don't be afraid of it. Don't be afraid. Like if I was doing it, I would do the slides first, I'll tell you all, but I'll always look back. Like what you see me doing today. Having read PowerPoint 1, I would look back at chapter 1. Having read PowerPoint 2, or maybe there's one part of it, like how today we focus on 3.1, 3.2, I would go and I would check it up, see if there's anything, is in and like more things in it then. But try to put it, and like I said, if you are not doing it, I am going to start doing it. I'm going to start, and I started today. I mentioned that at the top of the hour. I'm going to start, and then by chapter 4, by 5, we straighten the book, right? Because I want you to have the knowledge then, right? I want you to have that sort of knowledge. Anyway, it's 10 past 2. Let me go and try to finish off 3.2. And if you want, just look here, we'll see what we're going to look at. We're going to be looking at weld failures, non-destructive testing, and a couple of the techniques. Very short: dye penetrant, magnetic particle, eddy current, ultrasonic means, radiography. Maybe you could come back and read one or two, and then there's a same table. I put the same table for you all, the advantage and disadvantage of different types of tests, and that will be the end of 3.2. See how simple? See how simple, right? Let's look at it on the slide. I feel I'll come back and read one or two because I tell you that's the teaching technique from now on, to kind of, lean into a total look at the material at the book when we get into some, because if I don't do it, nobody will do it. If I don't do it, nobody will even open that book, right? I've started the same thing today. I have process safety after you all too. Today we're doing the same thing with them, but by chapter 4 for them is straight book as well, right? All right. Failure modes. Let me just bring this up here. So failure modes, right? Outline types of failure. So the strength of welded joints is dependent upon the type of joint and the quality of welding. I do think it depends on the quality of welding more anyway. But this is from your notes now. That's from your syllabus, right? The soundness of welding is checked by visual inspection, but more accurately by non-destructive testing. Other types of failure can occur from cooling after welding, and that is actually the annealing process. Residual stresses, the material probably didn't take the weld good, the molecules didn't, take it. Maybe there's some deformity to the structure of the metal itself, right? Poor material composition, maybe what he was working on was something with some high carbon in it, that doesn't weld very good. Exceeding the safe working load of the materials, or maybe the safe operating envelope of that particular type of metal, right? So visual inspection, use of the naked eye, magnifying glass, or a microscope or microscopy, limited to surface defects, can be time consuming and require good skill set by the operator. The inspector must have access to both each sides of the pipework or welded material. And that sometimes is dependent on the type of test that they're doing, especially so for radiography, right? I'll leave it for this slide when I reach it, right? I would explain it a bit more. So non-destructive testing, this is the use of testing for weakness in welded material without having to destroy the integrity of the component. So if you don't understand that, there is a test by destruction. Notice this is called non-destructive testing, but there is a test by destruction. You see it not too much in the oil and gas field or the safety world, but you see it in the automotive industry, right? Like a vehicle, a new version of it, changed to lights, bumper, sides of the engine and stuff, right? Airbags, seatings, where the seats are placed, doors, whatever, right? So the manufacturer of a vehicle then, right? What they normally do, and you all have seen it, they will crash a model of that car to see then what's the impact, like how soon does the airbags deploy? Are there any failures in the airbag system, right? What is the effect to the passenger? I mean, so it's a test by destruction, a destruction test, right? But of course, in the world of work, we can't really test everything by putting it under pressure. They do hydrostatic testing of tanks. They fill it with water and see if the tank could take the water. In a way that may be destructive because if the tank couldn't take the water, as what has happened, there was a case of that in Trinidad here at Trinma, company called Trinma. If the tank cannot take the weight of the water in it, right, then the tank would fail. So in a way that is destructive testing. But non-destructive testing is that you are going to sort of hire, like one of those NDT companies, and they would use one of these techniques on the joints and the welds and stuff to make sure that they don't see any cracks, right? And you have different techniques. You have surface techniques like dye penetration, magnetic particle is, I think, also surface defects. Eddy current, ultrasonic test is more like the metal itself, like a deeper look at the metal, radiography, pressure test, and all of those things are different types of tests to ensure that the material could withstand those kinds of tests, right? So it's 2:15, and we have some time. So let's go back to the book and we'll take this from the book, right? So I reached exactly where I thought I would have reached, which is good. Just where the book going now too. All right. So I have some nice videos on this, but we can today we'll stick to the technique being the slides, the book, right? For today. Maybe Wednesday I could show a video, or I could just send a video to the WhatsApp group, right? So non-destructive testing, so dye penetrant, involve the use of dye penetrants to highlight the defect so that the visual inspection is described above can occur. Dye is applied by spraying and this penetrates into the surface cracks. Dye absorb into the defects, indicate the location of the defect, right? It's a little bit more than that. I mean, I just reading what the book have here. Normally what they do, they apply a dye and then they put a developer. The developer is able to, like when you wipe off the dye then, like when you apply the developer, you'll actually see if the dye seep into the metal itself. And if it did, I mean, that's not supposed to happen because remember it's metal. If the dye seeped into the metal, it meant it have a crack there. You'll actually see like there's a crack and you see it with a dye. You see it colored, and if they color it purple or orange or whatever, they normally use like a bright color. So you can actually hold it probably under light, and you can see that the dye actually penetrated into the metal, which means that there's a defect there. Magnetic particle involves magnetizing the components by applying magnetic particles or ink. It's actually both. Any defects in the component will show as it distorts the magnetic field and the particles will lie differently, right? So the particle will kind of go to the place that it have the defect, right? So they can see then, okay, well, this is where they have the failure in the metal. I think I'll send you the video on it. It's about a half an hour long video, different types of testing techniques, right? After class, I'm gonna have to switch gears to process safety, but after class, if I could just go on YouTube, if I get the video, I'll just send it. I'll just share it to the WhatsApp group, right? The WhatsApp group. Eddy current, high frequency AC current passes through a coil, sets up alternating magnetic field. The coil is placed next to the surface of an electrically conducting material and sets up eddy current in the material. Any discontinuity in the metal surface causes a variation of the current that you see flowing. Well, they will have their what's the name of that meter? I can't remember the name of the meter. What come into my mind is anemometer, but an anemometer, but I don't think it's that. Um, I'm thinking too much safety. I supposed to be thinking electrical, right? Anyway, so the electrician will know the meter that they have, right? And they will see the difference in current value anyway. A second coil placed adjacent to the first can detect the change in the eddy current, so indicating the location of a defect. These changes can be calibrated and used to determine the depth of any defect. Ultrasonic involve the use of a generator transmitting ultrasonic waves into the material. That's a nice one, a nice little video on that, and detecting them with reflected forms within the material. Any defects will cause a variation in the return signal, and this can be interpreted to indicate the depth of the defect. It can detect defects within the materials and do not show on the surface. What is an ultrasound? Like, an ultrasound for a baby, right? Same sort of technology. Radiography uses X-rays and gamma rays. I'll stop, maybe we have pressure testing to do and then the differences, right? So involves gamma or X-rays that are passed through the material and onto a strip of film. Now, the strip of film is actually placed at the back of the metal, which is why in one of the notes it had the operator needed to access both sides of it, right? So X-rays, gamma rays, this is very good for like pipes and metal components. It's not too good for solid structures then, like if you couldn't go behind the metal, because in that technique, what they do, they have to put like a film, where's my marker? Right, so like a pipe that would have been worked on or welded on. This could be used, this could be great if this was the welded joint here, right? So the operator would have to come to the back there, if we call, maybe this is the front and not to the back. And what they will do, they'll wrap a film, like a photography film, for want of a better phrase there, right? And that's wrapped, well, to the front, to the back, but I just draw it in the back, right? But they wrap it in front too, and what they will do, the equipment they have then, right? The Geiger counter and stuff, the source of radiation then, right? They will actually shoot the rays into the metal surface here when they open it. When they say shoot the rays, they just have to open the equipment and the rays is going to penetrate the material and the film in the back, this piece of paper in the back then, that is where the image is going to be formed. It's like a photograph for film, right? So at the back there, you're going to see a pit here where you're going to see like, if any radiation penetrated, and radiation will penetrate, by the way, it will, because it's radiation. X-rays would penetrate metal, that's how they penetrate your bone, right? But anything that looks like you see a bunch of radiation, and I can see here looking darker, if I could draw that for you. If here was looking darker, it meant that more, it not drawing. I think I pressed it too much. Let me leave it a bit. I think it back, right? So if I could just draw that like that, right? So like here now, when you look at the film, if they realize, okay, there's more radiation there, but then it means then that somewhere here on this metal welding here, the radiation passed through more, right? So that's why they need, to get both sides access of the thing then, right? So look at right here, the radiation darkens the film emulsion, which when developed, a radiograph shows where any discontinuity or defects exist within the materials. This is important. This is an important method where a permanent record of the inspection is required. So this is good. You can show the company, look, we tested your thing and it seemed to have a defect. This part of the weld here, because this comes out like in the middle, that need to probably be welded over. You need to break out the weld and whatever and do it over, right? Okay, and is used extensively in steel fabrication, particularly in highly specific situations such as weld on oil rigs, pipework, and reactor vessels. I'll leave pressure testing for you because we spoke about like water testing a bit. You could read that one based on the time. You could just get it from the slide, but it's right there too, right? Let's do the advantages and disadvantages, right? So the following table summarizes non-destructive testing methods, visual tests, advantage, it's quick and inexpensive. You can actually get it done for yourself. The disadvantage is that it only checks surface defects. Surfaces must be cleaned and it must be accessible. To be honest, if you're doing this, you should probably just learn about maybe they say the one they like is actually the one with the x-rays, right? But you may want to be familiar with any other technique with dye penetrant, right? There are no whole questions then and things like eddy current, but there are whole questions on radiography then, right? Magnetic particle, maybe I can read that one, right? So more sensitive than dye penetrant, can also find subsurface defects. Ferrous metals only, so it's only used on metals then. It can't use on metals that don't conduct electricity, right? Cannot find defects at significant depth. It requires a power source, right? Let me go down to ultrasonic. Precise location of internal and external defects, sizing of many defects possible. So you can actually get the size of it, like what ultrasound could give you, the size of your baby or the gender of the baby. It's an ultrasound they use, right? How many of us have had that experience, right? Or you remember that experience there, Alicia? I remember my experience with it. Right? I always thought I was going to get a daughter. I don't know why. Always thought. And then when the ultrasound came up as boys anyway. All right. So the disadvantage of ultrasonic is that it is expensive equipment. You have to go to a technician or a technical company, dependent on the skill of the operator and a power supply. Radiography produces a permanent record, permanent pictorial, or that's the back of the film. You'll be able to get that. You can get the ultrasound too, so this may not always be true for all of them. Easily interpreted image, you can actually see the darkened spots and figure out, okay, that's where the defect is. Locates the majority of internal defects, right? Safety hazards is that you are messing with radiation, especially X-rays and gamma rays. Thickness limits, so more with X-rays or the thicker the metal, you may need to use a gamma ray, which is even a worse off radiation. Remember, these are the radiation that could be linked to cancer and have been linked to cancers, right? Power supply needed, need to access both sides of the pipe work. And remember, you need a technical skill here. This is going to be expensive. It's going to be a little bit more costly than using like a dye penetrant, right? Now, when I looked at the book a bit, I have a past paper too, but look at the time. Which one? Thinking which one to do. I'll just stick to the book, right? So when I looked at the book a bit, I realized they have some questions to the back of the chapter then, right? Well, to the end of everything. Outline the advantage and disadvantages of the different non-destructive testing techniques. And they say suggested answers at the end of the book, which is actually in this same publication as well. All right. But I mean, like, what is missing from this is the marks. I mean, that's the thing with some of these things, they don't have the marks with it. Like, we don't know if this is a 4-mark question or an 8-mark question or a 2-mark question, right? But the question itself is not a bad question, right? You can just pick. I would suggest to pick one or two and start learning. I would suggest the radiography first, this one here, and maybe dye penetrant, right? Those are the common ones I could think about for exam anyway. Should they say identify, first of all, define what is non-destructive testing. The non-destructive testing is a testing of the material, but you're not destroying the material, right? Unlike the crash cars then, or the manufacturers of the cars, they will crash their cars. Well, they crash the test model of the cars. They're looking for the register. The register quite on that side, right? I'll go for it in a bit. But so non-destructive testing is that you're tested, but you're not destroying the metal. And maybe two of techniques, name two techniques. And then advantages and disadvantages of the techniques anyway. Sorry, we run out of time. It's just how it is. I did kind of speculate we'd reach right here though. I did send 2018. If I could get it, I'll open it tonight. But I'll probably open it more on Wednesday. 2019 past paper as well. To see if we could find anything useful in them. Today, though, the technique was a bit different. I wanted to kind of get you into the book a bit for supplementary sake, right? And to know that some measure of that is going to be on you. Nothing too different if you realize if you look at how it was laid out here and how it's laid out in the slide. Of course, the slide is a PowerPoint, but it is a very good point then. It's a very good PowerPoint, to start from. But don't neglect the materials you have. Past papers are a great way to study as well. Handouts, great way to study as well. The internet, great way to study as well, right? Just give me a minute. I have to get the register from the other side of the room. I'll come back and I'll call the roll for you all. Right, I'm back. Right. So again, Wednesday, I will let you see where we are on the syllabus, right? Good and bad, right? We're not that far from the end. When I tell you at the start of today's class, I could finish chapter 5 in one sitting. Chapter 4 too. Those things are one sitting, folks. Those things are not the hardest. The last hard one is this one. The last long one is this one. Right? 4 and 5 in one week, one Sunday, one Wednesday. Right? All right, we'll stop here for today, right? Let me get the roll. Give me a minute, right? There's 9 of you, right? Okay, so we have Akash.
Present.
Thanks very much. Shadil Ryan is here. Rishad Thompson. I'm seeing you, so I'm gonna put you present.
Present.
Yep. Naveen. I see Naveen. Jessica. Yes, I see Jessica. I'm not seeing Nigel. Crystal is here. Alicia is here.
Present.
Christopher. Yep. Christopher Goben. Alicia Kayan.
Present, sir.
All right, folks, enjoy the rest of your weekend and the holidays as well. Alim is not here, but I saw him yesterday. He was by me yesterday, right? Stephen, I don't think is on the live. Raven. Devon said he couldn't be here. Didn't see Cohen Batiste either, right? All right, folks, we'll pick up on Wednesday. Anybody in the live didn't hear your name? Okay, if not, that's a wrap. I'll see you all back on Wednesday. All the best, everyone.
Quick question for you.
Sure. Yes.
Did my teammate drop the check for you yesterday?
I think he did. I believe he did. I had a coordinator. I can't remember talking to him. I spoke to him, so I guess yeah, he did.
I spoke to him yesterday morning. He said he would try to pass, but he didn't confirm if he did or not.
Well, I was teaching. So I guess he paid the coordinator because they
Okay.
were under the payment. But when I got a break, I had a break like around 2:30, like kind of like now. He asked some questions and I was talking to him about the ILO certificate, and he was kind of amazed that it wasn't what he thought it was. He thought that because he thought this like the NIBOS
Sounds like
cert
him.
there. Yeah. So I had to kind of show him on the syllabus. I took my phone, but eventually, that led into another student coming in, and then I think he kind of left. So I want to believe but I didn't interact with him other than the question he asked. But I want to believe he was there for
Okay.
that purpose. Only when I go back on Wednesday, I could check the payment sheets and see. But I think he did because he would not have come there to ask me a question on anything besides coming to pay. So I
Yeah,
want to say yes. Yeah.
definitely.
I want to say
His
yes. Yeah.
chance, man.
Yeah. All right. Okay. All right. All the best. Bye.